hold on. Okay, so this is going to be a short video for Hope, but I'm just going to let her know that so far today, we worked on vocab, and we watched the crash course video on stoichiometry. So we're working on chapter 9. And what's your question, Walken?
So the homework for tonight is re and second quiz, right? It's due
Tuesday, though, but yes. Yep. So, so it's page 225 to page 236, and questions 1 through 9, but that'll be due on Tuesday. All right, so basically what we're going to be doing in tomorrow's lab, I don't know if you guys have looked at it at all yet, but we're going to be doing 4 different reactions. I think one is a synthesis reaction, one is a decomposition reaction, and then there's a single replacement and a double replacement. So you guys will actually get to see all 4 of those in action, which will be pretty fun. All right. So we are in chapter 9, and we are looking at the mole. So now you guys hopefully understand a little bit as to why we have Mr. Mole here. He represents Avogadro's number. Very nice. So if you look at his little nameplate there, you can actually see Avogadro's number written out without the exponents, with all the zeros. So anyway, I'm sure you guys have all been wondering.
Yes.
You told us at one point.
Oh.
I had no idea what it was about.
Yes. Yeah, so the mole is here for a reason. The raccoon, I'm not really sure how that ended up here, but
Why not?
it's fun anyway. All right, so I'm on page 224. We have a intro to the chapter. Can I get a volunteer to read that? Sarah, wonderful.
Alright, creating critical chemicals. In a laboratory in Turin, Italy, a chemistry professor with a scarred face hid a secret. It was 1847, and Ascanio Sobrero had slowly stirred drops of glycerin into a mixture of hot nitric acid and sulfuric acid. He was terrified of what he had produced, and a thick liquid so explosive that it drove glass splinters into his face when he heated a drop of it in a glass test tube. His discovery was nitroglycerin. Sobrero hid his secret for a year. Just as Sobrero used sulfuric acid, H2SO4, to make nitroglycerin, other chemists in history have used it often in their work. Arab alchemists call it a mineral. Romans use it for medicine. In Britain it was used for dyes. It continues to be the lifeblood of our country's industry. In fact, the amount of sulfuric acid the U.S. produces is an indicator of its industrial health. American industries use sulfuric acid more than any other chemical except water. We use it to produce fertilizers, batteries, steel, paper, gasoline, medicines, dyes, and nylon. We need it to live and work. But sulfuric acid is extremely corrosive and gets very hot when dissolved in water. How can we mass produce this critical chemical safely and cheaply in its pure form?
Okay. All right. So, as we will learn, we'll be using sulfuric acid quite a bit in our calculations, and we also have quite a few labs that we use sulfuric acid. And I think I've said this before, but one thing you guys really seriously need to be mindful of, it is extremely toxic. The fumes can cause cancer, and it'll burn through just about anything. These desks, which are pretty dense. I do actually have one of the desks, I think it's that one there, has a couple of holes in it from
One of these ones does.
my first experience.
I have a tiny hole here.
Yeah,
so it's definitely something that we take seriously. We're not going to joke around or mess around or be horsing around when we have sulfuric acid out in the classroom, and you need to be extremely careful about not breathing in the fumes. So please don't take that lightly, because I would not want anybody to get hurt. All right, so our objectives for this section is to state Avogadro's number, which I think we've seen a couple of times now, and you guys at this point are experts at using exponents, right?
Yeah.
Yes, Andrew.
So it says Avogadro's number or whatever. So the Na down there, it's
just short for it when it says NA in parentheses?
Yeah, that's the symbol that you use for it. Yep. All right. So, and like a lot of our measurements, as he said, it's significant because it's an agreed upon unit. So it's not that it necessarily, it's a man-made number. It's made up. It doesn't necessarily represent anything specifically, but we use it to translate information from between scientists. Just like the periodic table, we have to have something that's universal that everybody understands. So the importance of Avogadro's number is that it allows us to give calculations of elements, which is especially important, when you have scientists around the world, say, working on a vaccine for a deadly virus. Being able to translate that information back and forth between different scientists is pretty essential for that, because all of those measurements have to be just right. All right. So the next thing is we need to calculate the mass, the number of particles, or the number of moles present in a given chemical substance when one of the quantities is given. So we have a couple of examples of that, which we'll probably have to get to, I guess, on Tuesday, because we're going to run out of time here, but we'll just go through the rest of these. So we need to distinguish between structural, molecular, and empirical formulas. So you guys will see all of that when you get into the reading, and maybe in some of your vocab you've already seen that. Calculate the percent composition of a substance when given the mass of each element. So for those of you that were paying attention in the beginning of the year when we did the percent error, it's a very similar formula that we use for that.
Oh, that's easy.
And then we need to be able to calculate an empirical formula from the percent composition of a substance. All right. So that's about all we have time for right now. I would highly recommend that you guys take your time reading through this material. Maybe read through it a couple of times. Pay attention to the example problems, because that's going to show you how to do these calculations. All right, and we'll do some of these together on Tuesday.